G'day cobbers, welcome back to the bush. In this episode of Lockups for All Driving, we're fixing the external plumbing of the Thumper Max II. We're going to replace this low flow standard outlet manifold with a custom copper high flow outlet manifold that anyone can build with basic hand tools at home. First up though, we need to understand how a reciprocating piston air compressor works. So let's have a look at that. On the left hand side we got the induction stroke, and on the right hand side we got the compression stroke. It's very similar in operation to the likes of a two-stroke engine. Now we've got the crankshaft here. Of course that's being driven by that electric motor that's sucking down those 90 amps. We have the conrod here and we have the piston here. Now as you can see, the conrod, the big end of the conrod, this is known as the big end and this is known as the small end, this is connected to that crankshaft but offset. So as this turns in the clockwise direction, this is being dragged down and therefore is dragging the piston down. When that happens, because of the seal in between the piston and the piston wall, creates a partial vacuum here. That then opens the reed valve and sucks air into the inlet. And now for the compression stroke. Now as the conrod big end moves past BDC or bottom dead center here, it starts moving back up towards the top. That in turn is pushing that piston back up towards the top. Now if we have a set amount of air inside that cylinder, but we're reducing the volume, it increases the pressure, and that's Boyle's law. When it gets to a certain amount of pressure, well, it'll open that reed valve and push it out the exhaust, and then we can do actual work with it, like inflating our tyres. And that's the basics of how a reciprocating piston air compressor works. And now we have a better understanding exactly how these piston air compressors work. Let's baseline this setup to find out how fast it turns with a standard outlet manifold. Now ordinarily, all I do is put a bit of reflective tape on the rotating assembly, point my digital tachometer at it, and Bob's your uncle. Unfortunately, our rotating assembly is under here and runs right through the middle there. I can't see it optically, but I can see it in other ways. And I thought to myself, well, perhaps using a pressure transducer like this one, I could see the peaks coming out of the outlet tube, one peak per cylinder per revolution. They'd be 180 degrees out of phase to one another. So all I'd have to do was look on the oscilloscope and measure the difference between three peaks, and then I'd have the time, and that would work. But then I thought to myself, hang on, I'd heard of this thing called a relative compression test, and what that does is uses a current clamp just like this one here in combination with an oscilloscope, and then all it does is it reads the amount of current the DC motor's taking. Now when the piston's heading up the bore, it takes more effort and therefore uses more current, and the same on the other side. So what I'll be able to do, and we'll shift to the screen in a second, is turn on the compressor for a second, freeze frame the output, and there we'd be able to measure in between our peaks and we'd have the revolution that this Thumper Max is doing. Okay, so let's turn on the Thumper Max and record exactly how much DC current this thing's consuming with the oscilloscope. So we can see our peaks here, here, and here. So this is one cylinder, this is the opposing cylinder, and this is back to the original cylinder again. So all I need to do is set up the cursor and type cross there, measure from this peak here to this peak here, and down the bottom here you can see that it's 5.4 milliseconds. Let's throw that into an Excel chart. I've just set this one up, so it's 5.4 milliseconds. There we go. And that tells us it's doing 11,111 RPM, 0.111. And here's the standard head in all its glory. They're the inlet ports there. On the reverse side, they're the exhaust ports. This is the cylinder side where the piston is. Using a vernier caliper, we can now have a look at what is the appropriate size pipe to use for our outlet manifold. Let's check it out now. So you've got two inlet ports and you've got two exhaust ports. The inlet ports measure about 6.75 millimeters across each, and the exhaust ports measure about 5.3 millimeters across each. That gives us a total inlet area of about 72 millimeters squared and a total exhaust area of 44 millimeters squared. And you'll notice the inlet is a lot larger than the exhaust. There's a reason for that. You have an ideal inlet to exhaust ratio of usually around 1.2 to 1.5 to 1. The reason that is when you're on the induction stroke, you only got atmospheric pressure, or 1 bar or 14.7 psi of pressure outside that cylinder, pushing air back in to fill up that vacuum. However, on the exhaust stroke or the compression stroke, you've actually got pressurized air pushing it out. So your exhaust port doesn't need to be nearly as big as your inlet port. Okay, now the inlet to exhaust ratio of the Thumper Max standard, well, that works out to be 1.6 or thereabouts to 1. So not too bad. But as I say, I can't leave well enough alone. We're going to have a look at how big exactly we can hog out these exhaust ports in order to get this Thumper Max pushing as much air out as possible. And here lies the rub. Whilst our exhaust port is 5.3 millimeters, we still have an O-ring here to contend with. And that's a problem because if we go drilling that out, let's say 10 millimeters, we're not going to have an O-ring sealing surface left and the thing's not going to work properly. Okay, the ID of that sealing surface is 7.5 millimeters, and we still need some material in between this point here and the edge of our port in order to support that O-ring. I figure I'm willing to go to 6 mil. So I'm going to drill these out to 6 mil and suck it and see. And I'll let you know in the description if it doesn't work for me. But that's still an increased area of around about 28%. And now we know the exhaust port size we're dealing with, we can start making intelligent choices as far as the inside diameter of the exhaust manifold we'll be fabricating. And here's our two freshly bored out 6mm exhaust ports. And that gives us a total exhaust area of about 57mm squared. Let's have a look at a couple of different options of copper pipe we can use to create this exhaust manifold with. 3/8 and 1/2 inch. Now 3/8 copper pipe has an ID of 7.7 mil and an area of about 47 millimeters, whereas 1/2 inch is about 10.9 millimeters ID and has an area of about 93 millimeters squared. So our 3/8 pipe will be 18% undersized. It will provide a restriction. What about our 1/2 inch pipe? Well, that's 64% oversized, so that should be fine, right? Or is it? It might actually be worse. Let's have a look why. And the reason is Bernoulli's principle. Now, Bernoulli's principle states when you go from a larger to a smaller cross-sectional area, the smaller cross-sectional area will actually increase the flow rate, but the pressure will drop off counterintuitively. And when we go back to a larger cross-sectional area, the pressure will increase and the flow rate will drop off. This is a water manometer, and all a water manometer does is it's reactive to the amount of pressure in the system. So if we have low pressure here, water goes up the column, and if we have high pressure here, water goes back down the column. So we'll flow some air through and see what happens to that water manometer. You'll see at this point here in the system, obviously the pressure has dropped off even though the flow rate has increased and the water has gone up the column. But you'll also notice a differential in height in between this point and this point here. Now the reason is we actually lose energy from the system when we go from one cross-sectional area to another cross-sectional area. We lose energy, and that means less efficiency, and that means our tyres are slower to pump up. So the takeaway from this is to minimize the number of cross-sectional area changes you have in the system, and of those cross-sectional area changes you have in the system, minimize the delta, minimize the size differential in between one cross-sectional area change and the next. Now, because I was using plumbing fittings to create the exhaust port, I decided to drill and tap the head outlet port to a standard plumbing fitting thread. And the one I chose was 3/8 BSP, and that stands for British Standard Pipe. It's actually a tapered thread, so it's self-locking, even though you've got to use a little bit of Teflon tape on them to seal them up. Now, 3/8 is 3/8 of an inch, but it's meant for 3/8 of an inch pipe, so the OD is actually much larger than 3/8. It's just over 16 mil, I think about 16.6 mil. So I had to drill it to 1932, or a scrap over 15 mil in metric, and that's what I'm doing here. And on with the tapping, and you'll notice the soft jaws in the vise so we don't damage the head. Now when you're tapping, you want to start that tap off in that hole as squarely as possible. They are more or less self-aligning, but you're doing yourself a favour if you start off square. Another thing to consider is the sides of that hole are parallel, but the tap is tapered, so it's going to get harder the further you bury that tap into the hole. And you'll notice me backing off every now and then, and that's to break the chip that's created by the edge of the tap. I'm also using a decent amount of lubricant. Ideally you'd use something like kerosene, but I think I've got a bit of CRC there, and that seems to be working fine. Periodically you're going to have to check the depth of the hole. Remember, it's a tapered thread, So you get your fitting and you wind it into the hole and make sure you're not too deep into that hole. And there you go, Bob's your uncle. 138 BSP thread in the King's Thumper Max head. Now let's show you some basics of using copper tube. Firstly, to cut copper tube. What you do is obviously mark up where you want the cut. Now this is a tube cutter. This is a much better way of cutting tube than a hacksaw. So you place the tube cutter approximately where you want to cut the tube, and all you do is run it around. Turn it around 2 or 3 times and then tighten up the nut a little. And keep doing that. Loosens up, couple more turns, and before long you'll have a nice clean cut in your copper tube. And there we go. Last thing we need to do, the outside edge is already deburred by the process of cutting. We need to use some form of tool, and this is a deburring tool, to deburr that inside edge. Okay, now we know how to cut copper tube. Let's have a look at how we're going to put bends in it. And here's a couple of different ways of bending that copper tube. Firstly, an internal spring. You can also get external springs. And they just fit down there, and then you can bend with your hands, because it's only copper pipe, to the radius you want. That's one way. Another way, and a little bit neater, is to use an actual bender. Now the way you use these is you put your copper tube inside the bender, and then grab your marker and mark off at your 0 degrees here. Let's say we want to put a 180 in this pipe. Rightio, so we need to get right around to the other side to 180 here. Now hopefully I've got enough copper pipe here. And all you do, because it's only copper tube, is bend it around. Usually I put it on my knee or in a vise. Okay, so I've cheated a little, taken it off the bench and used my knee. But I'll keep bending it around on the bench here now I can. And there we go. We're up to 180 degrees now. But the thing you would have noticed is it springs back a little bit. So what you need to do is you need to go just a little bit beyond that 180 degrees, and then you'll get a 180 degree bend out of that copper tube. I'll take off the former. And we'll pull it out. And there we go. A nice high flowing 180 degree bend in that copper tube. So now we can get on with making our manifold and soldering it up. So it turns out I accidentally deleted the footage of me soldering this thing together. So you just have to imagine me with a blowtorch and a bit of solder dobbing this thing together. But quite frankly, there are better tutorials than I can produce on soldering copper fittings to copper pipe on YouTube. Now guys, if you're enjoying this content so far, consider subscribing to the channel and ring that bell icon so you don't miss out on our future content. Now if you want ad-free early access to videos like this, consider becoming a patron on Patreon. Anyway, back to the episode. So we finished the soldering and we've screwed it back together. It's time to test the RPMs, just like before. Now theoretically, if this outlet manifold has less restriction than the standard, well, perhaps the RPM should shoot up a bit. We'll test that now. Okay, so we'll turn it on for a second again, and we'll check how many RPMs it's doing. There we go, we've frozen the oscilloscope, and let's head over and check it out. So just like before, here's one cylinder, here's the opposing cylinder, and we're back to the first cylinder again. So all we do is go to the cursor mode and we go to cross, measure in between this peak here and this peak here, and it turns out it's 5.06 milliseconds. Let's head over to Excel and punch that in. 5.06, and that's brought us up to 11,857 RPM. Let's compare the two. And here are the results of the outlet manifold RPM comparison. Standard, well, that came in at 11,112 RPM. Modified, Well, we got a slight gain at 11,858 RPM, and that's a 6.7% increase. Look, I'll take that, but I don't think we're going to realise the full benefit of our new outlet manifold until we actually port the heads. So as they say, the proof's in the pudding, so let's head outside and pump up that 35-inch tyre. And we're ready to test again. So the 5 volts coming out there, heading down to the pressure transducer, that's being read by the Manometer. Also got a current clamp here, that's also being read by the Manometer and displayed on the phone. We're at 18 psi, as you can see on the gauge. I'll start the logging and we'll head back up to 38 psi. Okay, that seemed pretty fast for me. We're back up to 38 psi. Let's compare the results. And here are the final results. Thumper Max II, stock versus modified outlet. On the left hand side we've got the pressure in PSI and the current in amps. Along the bottom here we've got the time in seconds. So this is 18 to 38 PSI with just the electrical mods, 44 seconds in that 35-inch tyre. And it's at around 90 amps right throughout the test. Let's have a look at the results with a modified outlet. 47 seconds. Actually nearly 3 seconds worse off. So I think what's happened here is it's like putting a set of race extractors on a standard car. You're not going to get any additional performance, you're actually going to be worse off. It's more suited to a modified ported head. Well, at least that's what I'm hoping, and we'll find out in the next episode. So what do we think in the end? Is the outlet manifold an epic fail? Well, we won't be able to tell until we modify these heads in the next episode. Now guys, if you like this video, give it a thumbs up. And if you didn't, by all means, give it a thumbs down. Not once, not thrice, but twice. Thanks guys. We'll see you in the next one.